So today we're going to be continuing with Chapter 8 on hypothesis testing, and we're going to take all the little concepts that we looked at in Section 8.1 and put it together into whole problems for hypothesis testing involving proportions. So for Section 8.2, we're going to be looking at how to test a claim about a proportion. Okay, like I said, we're going to be focusing on testing a claim made about a population proportion. So our claims are always going to be about a population something, a population proportion, a population mean, because we don't need to make claims about samples. We can gather and study samples, and we do that with the intention of being able to make generalizations to the population. So we test a claim that's made about a population, and in this case, proportion. So we can use this procedure when we're testing claims about population proportions, probabilities, or percentages. So we can use this procedure for all three of those. So what I've included here is an overview, flowchart, graphic organizer for hypothesis testing. So we're going to go through these steps here, and you can see that this is very much like the confidence interval chart that I allowed you to use on your test, and this is that it breaks it into proportion, mean with either sigma known or unknown, and then your standard deviation or variance type. You can go to Canvas and print this flowchart off so that you can have this used during this chapter. But the first thing we're going to do is learn how to identify the claim, identify the values in the problem, and then for today we're going to be doing the proportion type. We'll set up our null hypothesis using P as our population parameter. Then we'll check our requirements. If you notice, these requirements are the same as the ones for the confidence intervals, so you're not going to have to learn a new set of requirements. We've got our test statistic formula. We're going to calculate the p-value or critical value. I think most of you will find that the p-value is easier, but if you're used to doing critical values or for some reason just love critical values, then you're welcome to do the critical value method there. We'll learn how to draw our statistical conclusions, and then we're going to put it all together with our non-technical conclusions with that. So that's kind of the flow of the hypothesis test itself. So here are the steps that you're going to have to show in order to receive full credit on a hypothesis test. First thing that I want us to do is to underline the claim that's being tested. This is important, not just because it's the first step, but because it helps us to understand which type of hypothesis test we're going to do. And it also helps us when we start writing our conclusions and doing some of these other steps here. So underline your claim is the first thing. Use that underlined claim to determine which type of hypothesis test is being conducted. So for today, we're just looking at proportions, but as you can see, we're going to add some more to this. Identify any values that are given in the problem that you're going to need to work with. Verify the requirements for that type of problem. Identify your null and alternative hypothesis, which we learned how to do last class. Calculate the test statistic, which is just plugging into a formula. Find your critical value, or more commonly your p-value. We practiced that last class. Draw your statistical conclusion. That's just going to be either reject the null hypothesis or fail to reject the null hypothesis. And then the last step is the non-technical conclusion, and that's that 4-part flowchart that you write your conclusion from. Okay, so we're kind of going to go through these steps here on an example. So the first thing we're going to do, I want to make sure that you are familiar with all of the symbols that you'll need. Of course, N is your sample size, P is your population proportion, and it's the value that's used in the null hypothesis. Your P hat is X over N, or sometimes the P hat may be given to you as a percentage, but more commonly it's going to be given as X over N. And then this should be Q hat is 1 minus P hat. Okay, the requirements for this type is simple random sample as always, and then just as a review, it has to be binomial, which means that it's got a fixed number of trials. The trials are independent. You have the 2 categories, and the probability remains the same for all the trials. Your third condition is that N times P has to be greater than or equal to 5, and N times Q also has to be greater than or equal to 5. What that does is it allows the binomial distribution of sample proportions to be approximated by a normal distribution. Okay, so the test statistic that we're going to be using is z equals p hat minus p divided by the square root of pq over n. One thing, be careful that you group this numerator together. So if you just start typing straight across and don't group this together, you're probably going to get an error with that. And you also need to make sure that this is all grouped together as well when you put it in the calculator. Okay, so your p-values, we've looked at how to find those, and your critical values. So as far as some other methods, we've talked about the critical value method and the p-value method. Those two are going to be equivalent to each other, but another method called the confidence interval method, which we're not going to be using in this section, is actually not equivalent, and therefore we're not going to be looking at that due to time restrictions that we have. Okay, so we're ready to look at this example here. We have 1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54%, which is 545 of them, responded with no. Use these results to test the claim that most consumers are uncomfortable with drone deliveries. And so here is our claim statement. So I said we want to start out by underlining the claim statement. So our claim is that most consumers are comfortable with drone deliveries. Right. Most is implying greater than 50% or greater than 0.5 as a decimal. Okay, so here are the values that we want to identify in the problem. We can tell that this is a, one thing I didn't mention here as far as determining which type. If we're looking at the claim, as I mentioned on the previous slide, involved a percent. So when your claim involves some type of percent, that's going to be our proportion type hypothesis test. Okay, if we identify the values, of course, we need the sample size. X is the number of successes. So in this case, 545. We can find the p hat by doing X over N. And then the P is always going to come from your claim. So the value that's in your claim is going to be the P that we're going to use in the problem. Okay, as far as verifying our requirements, the simple random sample part, we're going to assume to be true there. It is binomial because either they are or are not comfortable with the drone deliveries, and it has the fixed number of independent trials and so forth. We need to verify that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. We know that the n is 1,009, the p is 0.5, and so if p is 0.5, q is also 0.5. So if we do those calculations, then we clearly get a number that's greater than or equal to 5, and therefore we've satisfied the three requirements that we have to do. Okay, the next step is to set up the null and alternative hypothesis. So for this particular one, we already talked about it's a proportion type, so our parameter is going to be p. The null hypothesis is the one that always gets the equal sign, and the value for the null hypothesis is always going to be the value in our claim statement. So I'm going to go back to our claim statement that we underlined, and that's why I said it's important to have this underlined so we can refer back to it. The value that we're using here is this 50% that was implied in the word most. And that's where the 0.5 is coming from that we use here. It's also important that we go ahead and identify which one was our original claim so that we can make writing our non-technical conclusion easier in the end. So our original claim was that, again, going back here, that most consumers are uncomfortable with drone deliveries. Okay, so if most are uncomfortable with drone deliveries, then that's actually going to match up with this alternative hypothesis here. So this is going to be my original claim. So as far as calculating the test statistic, we're going to use these values that we've come up with. So p hat is this x over n value. You can go ahead and substitute as a decimal. I would carry it at least 3 decimal places, if not more, when you put it here. The p is the one coming from the null hypothesis. And same thing as far as here, you're going to use the p and the q. It's not p hat and q hat as was on the confidence interval. It's actually just p and q, and then the n goes here. And so we get a test statistic of 2.55, and that's what we'll use to find our p-value. So for finding the p-value, we're going to put the 2.55 here on our graph, and we're going to find the probability of getting a test statistic of 2.55 or higher, which means this right tail here. So we'll do the normal CDF from 2.55 to infinity, 0 and 1, and we come up with a p-value of 0.0054. It's a right tail test, and we know that because if we look back at our null hypothesis, it's a one-tailed right-tailed test because of this greater than sign. So because it's a right-tailed test, we do not need to double this. This is going to be the p-value itself. And so as far as making our statistical conclusion, since the p-value, and this is our p-value, is less than the alpha, so that's the two things you want to compare. I always see a lot of people comparing different things. It's always p-value and the alpha that you need to compare. So in this case, the p-value is a smaller number than the alpha is. So if the p is low, the null must go, and therefore we're going to reject the null hypothesis. Okay, as far as our non-technical conclusion, I'm going to write these here so that I can reference them. We've got p equals 0.5 and p is greater than 0.5. And we had said that this was our original claim that matched up with our claim statement. Okay, so we said that our conclusion was that we're going to reject the null hypothesis. So if we're rejecting the null hypothesis, that means we're going to have to throw this one out. And we're throwing that one out in favor of this one, which means that we're able to support this one. So we would say there is sufficient sample evidence to support the claim that more than half of consumers are uncomfortable with drone deliveries. So anytime our original claim is in the alternative hypothesis, we are going to make a statement that involves whether we are or are not able to support the claim. Okay, so here is another look at that chart. This particular one, it did not contain the condition of equality because the claim was not in the null hypothesis. So we said that we're going to reject the null hypothesis. So we have this, and that is equivalent. The sample data supports the claim is equivalent to there is sufficient sample evidence to support the claim. So the wording of those it's irrelevant which one of the two you use there. They're both going to mean the same thing. And this is just kind of the simplified version of that. So to do this problem on the calculator, what we're going to do is we're going to go to stat. We're going to go over to test. And this time we're going to go down to one proportion z-test because all these first 5 here are hypothesis tests, and then we start with the intervals are the confidence intervals. So we're going to choose number 5. That's going to bring up these prompts here. So the first prompt, you're going to put in the value that you use for your null hypothesis, which for us was 0.5. The x was 545. The n was 1009. And it was a greater than. So we're going to put calculate. And what we see is that we can see that this is our alternative hypothesis that we're testing. The 2.55 is our test statistic that we had found. Here's our p-value, and the calculator does go ahead and double that if it needs to be doubled, so you don't need to double this a second time. And you can see your p-hat and your n. So it's not going to draw the conclusions for you. It's just going to give you the test statistic and the p-value to allow you to make your conclusions. Okay, if I was going to do this same problem in StatCrunch, I would go to Stat, and then I'm going to go down to Proportion Stats, one sample, and this one I have my summary statistics. So here for the number of successes, I'm going to put the 545. For the observations, that's your sample size, so 1009. Your null hypothesis, you want to put in the 0.5. Here we want to change that to greater than and compute. And what we see here is our null hypothesis, our x and our n, our p-hat, our test statistic, and our p-value is all given to us there. So if we want to do this same problem using the critical value method, steps 1 through 6 are the same. So the only place we start differing at is where before we calculated the p-value, here we're going to come up with our critical values. So to find the critical values for this one, We were told that we had an alpha of 0.05 when we started the problem. So we're going to put 0.05 in this right tail. And again, we know it's a right tail because our alternative hypothesis was P is greater than 0.5. So that tells me it's a right tail test. So this is where this is going to be my rejection region here. I just need to find this critical value. So I'll find the critical value by doing the area to the left here. So if this is 0.05, that leaves me with 0.95 over here. So I'm going to do the inverse norm of 0.95 and I get 1.645. So what that tells me is anything larger than 1.645 is going to be in the reject region. Anything less than 1.645 is going to be in the fail to reject region. Okay, so our test statistic that we had calculated was 2.55. So 2.55 is going to be over here, and therefore it's going to fall in the reject region. So our conclusion is the same as what it was with the p-value. It's just a different approach to doing it. The critical value method, sometimes called the traditional method, relies a little bit heavier on the tables that were historically used for doing this. But now that we have more calculators and computers to generate different p-values, it's actually much easier just to do the p-value method than the critical value method. Okay, so this is just kind of a visualization of the rejection and fail to reject regions. Okay. So, so our conclusions should be consistent with each other, which they are. All right, so sometimes you have to find the number of successes. So maybe they tell you that a certain percentage and you have to find the number of successes. So we'll find the number of successes by multiplying n times p hat. So that's something we're going to need for this next example when we get started with it. So here we have a study of sleepwalking or nocturnal wandering was described in Neurology magazine, and it concluded information that 29.2% of 19,136 American adults have sleepwalked. What's the actual number of adults who have sleepwalked? So this is where to find the actual number out of this 19,136, we're going to have to say that x is n times p hat. So we're going to have 19,136 times the 0.292, which was our sample proportion here. So if we multiply 19,136 times 0.92, then we're going to get 5,587.7. And the x is always going to be a whole number, so we're actually going to round that to 5,588 for our answer there. Okay, so we want to test the claim. So we just did this first part here. That's the actual number of adults who have sleepwalked, 5,588. We want to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 0.30 with a significance level of 0.05. So with this, the first thing that we want to do is to identify our claim statement. So we want to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 0.30. Okay, so that's the claim that we're testing. And because we're testing a claim about a proportion, then that tells me the type that we're dealing with. So we're dealing with the proportion type. As far as getting some of the information that we're going to need, this is going to be our sample size, our n. This is our p hat, and this is our x that we're going to need, and this is our alpha. So I'm going to recopy some of that to the next slide so that we can get started. So we said our n is 19,136. Our alpha is 0.05. Our p hat is 0.292. That's coming from the 29.2%. And our x is 5,588. And one thing that we failed to mention is the p. We can actually get the p because the p is going to come from our claim statement. So our p is going to be 0.3. Okay, so we've identified all of our values. The next thing we want to do is to check our requirements. Okay, so we said it's a proportion type, so we need to know that it's a simple random sample, that it is binomial, and that n times p is greater than or equal to 5, and n times q is greater than or equal to 5. So we're going to assume it's a simple random sample. As far as binomial, this particular one, we have our two categories, either they have or have not sleepwalked, and they're independent, our probabilities are not changing, and so forth. So we basically have the requirements that we need for the binomial. For this one, for n times p, n is so large, we're really not going to have any problems here, but our p is 0.3. So if I multiply that out, then what I'm going to get is 5,740.8, and clearly that's greater than or equal to 5. Here, q is going to be 1 minus p, so that's going to be 0.7. So I'm going to have 13,395.2, and that's also greater than or equal to 5. Okay, so we're ready to move on and set up our null and alternative hypothesis. Okay, so our null hypothesis for a proportion type, it's always going to be p. We know the null is equal, and the value that p equals is coming from our claim, and that's 0.3. Okay, so looking back at our claim here, the claim is that the proportion of those who have sleepwalked is less than 0.3. So that's where we're going to put our less than sign here. Okay, we're ready to move on to our test statistic. So our test statistic, we're going to have z equals p hat minus p divided by the square root of pq over n. So p hat is, and that's why I like to have everything outlined here. It makes it easier once we get started. We're going to have 0.292 minus the p, which is 3.3. Right. Here is the p, which is 0.3. The q is 0.7, and the n is 19,136. Okay, when we put all of that in our calculator, make sure that you put parentheses here and that you also have all this grouped within the radical. And so we end up with negative 2.41 as our test statistic. Okay, so when we look back here, we see that this is a less than. So this is going to tell me that is a left-tailed test that I need to find. So I'm going to find my p-value next. Okay, so here I have negative 2.41. It's a left-tailed test, so I'm going to shade in here. So I'm going to do a normal CDF, and that's going to go from negative E99 to negative 2.41. So I'm going to get, for my p-value, 0.0080. I don't need to double it because it was a one-tailed test. Okay, so for my statistical conclusion, I need to compare the p-value and my alpha. So the p-value I found is 0.0080, and my alpha is 0.05. So my p-value is a smaller value than the alpha, and if the p-value is low, the null must go. So my statistical conclusion is that I'm going to reject the null hypothesis. Okay, as far as the non-technical conclusion, which is the last part of this, we need to figure out where our claim statement is. So if I look back, the claim is the one that said it was less than 0.3. So that's going to be this statement here that is saying less than 0.3. So we always want to look and see which one of these is saying in symbols what our claim is saying in words. And that's going to be our claim statement. So this is our claim statement here. Okay, so if you follow along with the chart, what you're going to see is that for this particular one, our claim did not contain the condition of equality because it was an inequality here. Our claim was not in the null hypothesis, another way to think of that. So we're going to be talking about whether or not we support the claim, and since we're choosing to reject the null hypothesis, We're going to reject the null hypothesis in support of or in favor of our alternative hypothesis. So we would be able to say there is sufficient evidence to support the claim that those that have sleepwalked is the proportion of those that have sleepwalked is less than 0.30. And this is another reason why underlining your claim is important, so that you can wrap back around to the beginning, to that claim statement pretty easily, and wrap your problem up. Okay, so our statement, if you want to see it written out here, we conclude that there is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked. So the remainder of today's lecture, we are going to just be practicing more of these problems to help you get more used to the process. So at some point, hopefully you're going to get comfortable enough that you can try it on your own. If you feel that way at this point, then try this one and check your work. If not, then stay with me and listen to the video, and we'll see how you do with it. Okay, so this problem, a trial was conducted of the XSORT method of gender selection, and that's just a gender selection method to help people be able to have baby girls or baby boys. I think in this case it would be baby girls. So among 726 babies born to couples using the XSORT method in an attempt to have a baby girl, 668 of the babies were girls and the others were boys. Use these results with a 0.05 significance level to test the claim that among babies born to couples using the XSORT method, the proportion of girls is greater than the value of 0.5 that's expected with no treatment. So basically what we're trying to figure out here is, are these results convincing enough to say that the XSORT method is working? That's what we're really testing. So looking at this, we've got 726, that's going to be my N. So out of those 726, 668 had girls. So that's going to be my X. We're going to use the results with a 0.05 significance level. So this is my alpha. And we want to test the claim that among babies born to couples using the XSORT method, the proportion of girls is greater than 0.05 that's expected with no treatment. Okay, so we're basically ready to get started. Here, if I look at this claim statement, it's a claim about a proportion. So this is going to be a proportion type problem. I'm going to go ahead and transfer this information over. This is going to be my p-value. I shouldn't say that like that. This is going to be my p that's going to be in the null and alternative hypothesis. It is not the p-value. There is a difference between those. Okay, so N in this one is 726, X is 668, and alpha is 0.05. P is 0.5, and we can find p hat by doing x over n. So 668 over 726 gives me a p-value of 0.920. So usually go at least 3 decimal places for the p hat on this one. Okay, so for the requirement check, we're going to assume it's a simple random sample. And it is binomial because either they're boys or girls. So we've got those two. And the third one is that N times P is greater than or equal to 5. We need to show that. So 726 times 0.5 gives me 363, and that's greater than or equal to 5. N times Q, that's 726 times 0.5 again. So the same thing, and we're definitely greater than or equal to 5. So we've got our requirements fulfilled. So we're ready to go ahead and set up our null and our alternative hypothesis. So our null hypothesis and alternative are going to use the parameter p because we're doing proportion type. If we look back at our claim statement here, the claim is that the proportion is greater than 0.5. So 0.5 is the value that we're going to use, and greater is going to be the symbol here in the alternative. And because this statement here is the one that matches up with the claim, then we're going to denote that as being our claim statement. And because specifically our claim said the proportion is greater than, so if we translate that to mathematical symbols, then the alternative is the one that's saying that for us. Okay, so for our test statistic, we're ready to calculate that. So we're going to have z equals p hat minus p divided by the square root of pq over n. So here we're going to put 0.920 minus 0.5. We're going to divide that by the square root of 0.5 times 0.5, and then 726 for n. So when I calculate that, I get actually a very large test statistic. So this is actually going to be very convincing evidence in terms of testing this XORT method. If you get a Z value that is beyond 3, that is extremely unusual. So to have one as high as 22.63 is very unusual to have there. So when we go up and continue with this problem, the p-value to find that, if I look at this, 22.63 is actually way out here in the right tail. We do know it's a right tail because if we look down here at the alternative hypothesis, it's a greater than. So greater than indicates it's a right tail test. So we're going to do the normal CDF from 22.63 to infinity. Our mean is 0 and standard deviation is 1. So when we put that in, what we're going to get is 0 plus. It may even show 0 on your calculator, but we know that 0 plus indicates it may not be totally impossible, but it's pretty close. So if we compare the p-value and the alpha, my p-value was 0 plus, my alpha was 0.05. So if the p-value is smaller than the alpha, then we're going to conclude that we reject the null hypothesis. So this is my statistical conclusion. So the last thing I have to do is to do my non-technical conclusion. So for the non-technical conclusion, I'm going to go down here, and we decided to reject the null hypothesis. So we're going to reject that null hypothesis in favor of the alternative. So we're going to say there is sufficient evidence to support the claim that, and I'm not going to write it all out, but the claim, there is sufficient evidence to support the claim that among babies born to couples using the XORT method, the proportion of girls is greater than the value of 0.5 that's expected with no treatment. So in other words, we do have evidence to say that the XORT method is working. Okay, again, if you wanted to put that in on your calculator, then this would be how you would do that. Okay, so we have another one here. Again, if you feel comfortable, go ahead and pause it and try this one. If not, then follow along. Okay, a dietitian claims that 60% of people are trying to avoid trans fat in their diet. She randomly selected 200 people and found that 128 people stated that they were trying to avoid trans fats in their diet. At a significance level of 0.05, is there enough evidence to reject the dietitian's claim? Okay, so here is her claim that 60% of people are trying to avoid trans fat in their diet. So if I look at this, I've got, here's my N, my sample size. Here's my X. Here's my alpha. And this is actually my P. And so I'm pretty much ready to go with it from here. I look at my claim and I see the claim is about 1%. So that tells me it's the proportion type. So if I identify my values, I've got N is 200, X is 128, alpha is 0.05. P always comes from the claim, so that's going to be 0.60. And P hat is X over N, so 128 over 200. And that's going to give me 0.64. Okay, for the requirement check, we've got simple random sample. We're just going to assume to be true. Binomial, we've got our two categories. Either they are or are not trying to avoid trans fats in their diet. if we want to show, and we need to show the n times p, so n is 200 and p is 0.6, so that's going to give us 120, and that's definitely greater than or equal to 5. N times q is going to be 200 times q is 1 minus p, so 0.4. So that's going to be 80, so that's greater than or equal to 5. So both of those we're good on. So okay, our next step is to set up our null and our alternative hypothesis. So on this one, it is a proportion type, so it's going to be P, and the value that we see in our claim is what's going to be used in our null and alternative, so that's 0.60. And we don't really indicate a direction on this, so we're going to use a does not equal here. So when we look at the one of these that matches up with our claim statement, it's actually this first one, this null hypothesis, that's our claim on this one. Okay, so now we'll calculate our test statistic. So the test statistic is p hat minus p divided by the square root of pq over n. So we'll have 0.64 minus 0.60 divided by the square root of 0.6 times 0.4 divided by 200. Okay, and so when we calculate that, we get 1.15. So that is a much smaller test statistic than the one from the previous problem. So here we've got 1.15. This is a two-tailed test, so I'm going to find this, and then keep in mind that I also have one over here. So I'll do a normal CDF from 1.15 to infinity. Okay, when I put that in the calculator, I get 0.1251. And since it's a two-tailed test, and I know that because of this does not equals here, so if it does not equal, it's always a two-tailed test, I'm going to need to multiply this by 2 to get my p-value. So my p-value is 0.2502, and that's going to be my p-value. Okay, so I'm going to come back up here and do my comparison. So I'm going to compare the p-value to my alpha. So the p-value I found to be 0.2502. The alpha was 0.05. So my p-value is larger than my alpha. When that happens, my conclusion is going to be that I failed to reject the null hypothesis. So in failing to reject the null hypothesis, I'm actually going to have to hold on to this. Okay, so I failed to reject it, so I'm going to have to hold on to it. So what I'm going to say is there is not sufficient evidence to warrant rejection of this null hypothesis, which happens to be our claim. So there's not sufficient evidence to warrant rejection of the claim that 60% of people are trying to avoid trans fats in their diets. So we're not saying that we believe the 60% to be true. We're just saying that based on this sample, we don't have evidence to reject it. That's all that we're really saying there. Okay, so this is the statement. If you want to see it written out, there is not sufficient evidence to warrant rejection of the claim that 60% of people are trying to avoid trans fat. Okay, so here's another one. I would certainly at this point recommend that you're trying these on your own and then seeing how you should be doing them. Okay, this one, an attorney claims that more than 25% of all lawyers advertise. So here's our claim. A sample of 200 lawyers, so this is going to be my N, in a certain city showed that 63, so this is my X, had used some form of advertising. At a alpha equals 0.05, is there significant evidence to support the attorney's claim? So we have our claim statement. The claim statement contains a percent, so that tells me it's a proportion type hypothesis test. And if I summarize my information, N is 200, X is 63, alpha is 0.05, P is coming from the claim statement, so that's 0.25. P hat, we're going to need to calculate as X over N, so 63 over 200 is going to give me 0.315. Okay, for the requirement check, we're going to assume it's a simple random sample. It is binomial in nature because either they do or do not advertise. We've got our two categories. And then N times P, that's going to be 200 times 0.25. So we get 50 there, and that's greater than or equal to 5. N times Q, so 200 times 0.75. Remember, Q is 1 minus P. It's going to be 150. Okay, so from here, we're ready to set up our null and alternative hypothesis. So all these we're doing today are proportion types, so they're all going to be P's. Now, next class, we're going to add a different type, so it's not going to keep being P's. But for now, these are all population proportions that we're comparing. So the value that we use comes from our claim, so that's the 0.25. And we're saying that more than 25%, so that's going to be greater than. So now we're ready to do our test statistic. So we're going to calculate the p hat minus p divided by the square root of pq over n. I always like to write this out because it keeps me organized. So p hat is 0.315. I'm going to subtract from that the p, which is 0.25, and then divide that by the square root of 0.25 times 0.75 divided by 200. So when I do that calculation, I'm going to get 2.12 for my test statistic. Okay, now finding the p-value, we've got 2.12, and this was a right-tailed test because we have the greater than sign. So I'm going to do the normal CDF from 2.12 to infinity. And I'm going to get for that 0.0170. And since it's a one-tailed test, this is the p-value. I don't need to double it. So I'll compare the p-value and the alpha. So my p-value is less than the alpha. So when the p is low, the null must go. So I'm going to reject my null hypothesis. Okay, so my statistical conclusion is that I reject the null hypothesis. When I look over here at this alternative hypothesis is the one that actually matches up with my claim statement because it's saying more than 25%, which would indicate the greater than symbol. So this is my claim, and we are saying that we're going to reject the null hypothesis in favor of or in support of this alternative hypothesis. So we'll say there is sufficient evidence to support the claim that more than 25% of all lawyers advertise. As far as following the flow chart goes, if you ask the question, is the claim in the null hypothesis? No, it's not in the null hypothesis. And then if you follow the rejection part to the flow chart, it's going to take you to that statement that I just said, which if you want to see it written out, there is sufficient evidence to support the claim, or the sample data supports the claim. You just mainly need to have the word supports in there. So it supports the claim that more than 25% of all lawyers advertise. Okay, last example here. Again, try this one and see if you can get it on your own. Okay, a telephone company representative estimates that 40% of its customers have call waiting service. To test this hypothesis, she selected a sample of 100 customers and found that 37% of them had call waiting. At a 0.01 significance level, is there enough evidence to reject the claim? So looking at this one, the telephone company representative estimates that 40% have call waiting. So this is the claim that we're testing here. And we've got this 40%, so we know it's a proportion type because it has the percent in the claim. And as far as our values go, we have an alpha of 0.01. We have a sample of 100, so that's my N. This value is coming from the claim, so that's going to be my P. And instead of giving us an X this time, they actually give us the P hat. So the P hat is already calculated for us, and that's 0.37. Okay, we're ready to look at the requirement check now. So we've got simple random sample, binomial because either they do or do not have the call waiting service, and then N times P. N is 100 and P is 0.37. Sorry, P is 0.4, not P hat. So this is 40, and that's definitely greater than or equal to 5. N times Q, that's going to be 100 times 0.6. So 60, and that's greater than or equal to 5. Okay, so we're ready to set up our null and our alternative hypothesis. Okay, so what we know there is that our parameter is P for the proportion type. The null is always the equals one, and the value that it equals comes from the claim. So that's going to be the 40%. And we're testing a claim that estimates that 40% of customers have call waiting service. So here, this will be a does not equal because it's not indicating a direction. When we look back at our claim statement, the one of these mathematically in symbols that represents the claim is going to be this one. Okay, so for our test statistic, our Z is, and I'm running out of room here, so I'm not going to write the formula out, but it's going to be P hat minus P divided by the square root of P Q over N. Again, remember, if you're not getting these to come out right on your calculator, then you need to make sure you're putting parentheses around these. So if you do this, then you're going to see that Z is negative 0.61. So if I look at the p-value for this one, we're going to be over here at negative 0.61. This is a two-tailed test because it's a does not equals. So I'm going to do normal CDF from negative E99 to negative 0.61. And I'm going to find that when I put that in the calculator, I get 0.2709. And because it's a two-tailed test, I've also got an equal area on this side. So I'll multiply that by 2, and that gives me 0.5419. And that's going to be my p-value. You can probably already see that that's a fairly large p-value. So if I have 0.5419 and I compare that to my alpha, which is 0.01 that they're giving me here, clearly my p-value is larger than my alpha. So because of that, my conclusion is going to be that I failed to reject the null hypothesis. And as far as the final conclusion here, if I'm failing to reject the null hypothesis, that means I'm going to have to hang on to it. So what I'll say is there's not sufficient evidence to warrant rejection of the claim. So anytime my claim is in the null hypothesis, I'm not going to talk about whether I support the claim. I'm going to talk about whether or not I can reject the claim. So again, that goes back to that flow chart, but we would say on this one, there is not sufficient evidence to warrant rejection of the claim that 40% of its consumers have call waiting. One thing I noticed here is that this should be 0.4 and this should be 0.6. So just make sure that you do make those corrections. They were correct on the previous in the previous information, but just make sure you make those corrections there. Okay, and that takes us to the end. So you've seen several examples that show you how to use hypothesis testing when you're talking about proportions. Next class, we'll start talking about a hypothesis testing for means. The good news is we follow these same steps over and over again with just slight variation. So if you really understand this, you should be good for the next class. I know today the last two lectures have been pretty long, but we just had a lot of information and I wanted to include plenty of examples. So thank you and have a good day.